Hey everybody, welcome back to another lecture video. In this chapter, 15, we will be looking at chemical equilibrium. Okay, so let's just jump right in. So you may remember from our discussion on evaporation, I think this was chapter 12, we talked about a type of dynamic equilibrium. We said that when in a closed container, water is evaporating, or a substance, a volatile solvent or substance is evaporating, that it evaporates to a point where the concentration in the vapor form gets high enough that it starts to recondense, and that these two processes eventually equal out so that we get a constant vapor pressure. So the evaporation and then the condensation reach a dynamic equilibrium. So a dynamic equilibrium involves two opposite processes that occur at the same time. So in this image, there's an analogy between a chemical equilibrium. So let's say that we have, oops, what's going on here? Sorry, I'm trying to get my pen to work. Okay, here we go. Sorry about that. So, chemical reaction, let's say like N2O4, that will decompose into two molecules of NO2. And if two molecules of NO2 find each other, they can actually come together to make N2O4. So these two opposite reactions are occurring at the same time, at the same rate, and this is an analogy with a freeway with traffic moving in opposite directions at the same rate. So it's not a static equilibrium, which would mean that there's no change in either direction, but also things stop moving, right? The freeway would always look like this, even though the actual cars are constantly changing. There's never the same cars, right? They're not the same people. This car will eventually go all the way down the road and then disappear. So that's why it's a dynamic equilibrium. It's equal in that it looks the same, and that the rates and the concentrations will stay the same. There's always going to be this many cars on the freeway. They won't be the same cars. So that's where the term dynamic comes in. So let me remind you a little bit more about equilibrium in case that you guys have kind of forgotten. It's been a couple chapters. So we can think of equilibrium as sameness or constancy. Okay? When an object is in equilibrium with its surroundings, the property of that object has reached sameness with the surroundings and is no longer changing. So for example, a cup of hot water. Right? A cup of hot water is not in equilibrium with its surroundings with respect to temperature. If you leave it undisturbed, though, this cup of hot water will slowly cool until it reaches equilibrium with its surroundings, and at that point, the temperature of the water is the same as that of the surroundings. So there's where our sameness happens, and it no longer changes, and that's where the constancy part comes in. So sameness, constancy. Now, part of the definition for living things is that living things are not in equilibrium with their surroundings. This is why a cup of water is not a living thing. It does reach equilibrium with its surroundings, at least in the temperature sense. Our body temperature is not the same as the temperature of our surroundings. Living things, even simple ones, can maintain some sort of disequilibrium with their environment, whether that's concentration, disequilibrium, cells having sugars on the inside and there not being sugar on the outside. Nature wants everything to spread out. And so we kind of use this definition when we are deciding if something's alive or not. Now, we add the concept of control to complete our definition of life in terms of with respect to equilibrium. A cup of hot water, as I mentioned, is not in equilibrium, or not in disequilibrium with its environment, yet it's not alive. The cup of hot water has no control. I'm sorry. The cup of hot water will eventually reach equilibrium. But when it's hot, it is in disequilibrium, right? but it can't control that. It can't keep it that way. And that's why we would say a cup of hot water is not alive, because it has no control over staying hot. Whereas in contrast, living things can control that. You may not do it consciously, but your body maintains your temperature within a specific range, and that is not equilibrium with the surroundings. So one definition of life is that living things are controlled disequilibrium with their environment. Okay, and then a living thing, of course, does come into equilibrium with its surroundings eventually, right, after one dies. Okay, so the rate of a chemical reaction, let's talk about that real quick. We examine the concept of equilibrium, especially chemical equilibrium, the state that involves sameness and constancy. Reaction rates are related to chemical equilibrium because a chemical system is at equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. So that's why when we draw these things, we often show those forward and backwards arrows. I'm going to go back to my N2O4 example. So the rate of the forward reaction reaches the rate of the backwards reaction. Now, the rate of a chemical reaction, a measure of how fast the reaction proceeds, is defined as the amount of reactant that changes to product in a given period of time. In a reaction with a fast rate, the reactants react to form products in a very short period of time. In a reaction with a slow rate, the reactants react to form products over a long period of time. Okay? Reaction rates can actually be controlled if we understand the factors that influence them. Now, collision theory is something that we're going to talk about. Now, chemical reactions occur through collisions between atoms or molecules, right? So there's a molecule of NO2. I'm just going to draw NO2. I'm not going to draw the Lewis structure. Now, these have to collide together with the right energy and the right orientations in order to react. If the collision occurs with insufficient energy, then they just bounce off each other without reacting. If they do have enough energy, and the molecules are colliding fast enough and in the right direction, right, facing the right way and all that, then the reaction can proceed. Now, since gas phase molecules have a wide distribution of velocities, meaning some gas molecules have lower energy than others, at a given temperature, collisions actually occur with a wide distributions of energy. Some collide with not enough energy, some collide with more than enough energy. Now, high energy collisions lead to products. Low energy collisions do not lead to products. Higher energy collisions are more likely to lead to products because the most chemical reactions have what we call an activation energy. We usually describe this or show this with a little graph. So we have, let's say, the energy of our reactants. This is the energy line right here. This is the energy of our reactants. And then this is the energy of our products. And so we're going to convert something which has, this much energy into something that has this much energy, lower in energy. And that's how nature tends to want to do spontaneous reactions. Now, the problem is, though, that you see that the energy hump does exist. There's a hump there. You can't just drop straight down. And so that means there's actually some amount of energy that we have to put in to get this reaction to happen. And that means, again, having them, their bonds need to be broken so that they can form new bonds. That energy might be the speed that it's going to take for them to collide, the orientation, this and that. We're not going to go into all of those terms here because it's beyond the scope of Chem 20. But that's the activation energy. Now, the activation energy, as I mentioned before, can be consisting of a few different things. Now, if molecules react via high-energy collisions, then the factors that influence the rate of reaction must be the same factors that affect the number of high-energy collisions that occur per unit time. The two most important of these factors are the concentration of the reacting molecule and the temperature of the reaction mix. And that should make sense, and we'll take a look at both of those. So first, let's look at how concentration affects the rate of reaction. Now, the rate of a chemical reaction generally increases with increasing concentration. The exact relationship between increases in concentration and increases in the reaction rate vary for different reactions, and that's the subject of chemical kinetics, and we're not going to go into that. There's a lot of different factors that matter, for like the molecularity. And again, this is a term, you can Google it, but this is how the reaction takes place. Is it two molecules reacting together? Is it three molecules reacting together? Is it one molecule that reacts with itself? These kind of things. That's just one of the terms. There's frequency factor. There's others, but and then of course there's reaction order, which we're not going to go into at all. So it's not enough to just say if we double the reaction or if we double the amount of hydrogen that we're going to double the rate. Okay, if you take Chem 1 in the future, you're going to see that that's not always the straightforward relationship. But here in Chem 20, we don't need to go that in depth. All we have to say is when we increase the reaction or the concentration of reactants, the rate will go faster. And that is true. We can't say it'll double or triple or give you any other rules, but it will. And let's look at why. So, number of collisions, right, in a low concentration system. Let's just say that that's the initial low rate. And then if we start to add more molecules, well then those collisions are going to take place more often, right? Let's say everything else is the same, temperature's the same, size of the container's the same. They're gonna be seeing each other more often, so they're therefore colliding more often. Now we may get some more unwanted collisions, like hydrogen gases reacting with themselves more often, but on average, more often we will see the two reactants in that equation reacting together. So we will get a faster rate. Now, increasing the concentrations again or even further just means that they are going to see each other more often. Because even if only 5% of these guys are reacting, then, and so if that's 100 molecules, 5% of that is 5 molecules. So if we increase it to 1,000, right, that's 50 molecules. So right off the bat, still 5% is still 5%, but it's a lot more. So that should make sense. The other thing that will affect reaction rate is temperature. Now, raising the temperature makes the molecules move faster. So you can see here, if we have a low temperature, let's say the concentration stays the same throughout, more collisions per unit time will result in a faster rate because more collisions are happening, and so we'll see that product forwarding faster. A higher temperature results in more collisions that are of higher energy also. Higher temperature means that these molecules have more energy as they move around. So that's always going to make it go faster. Now, that's not the case for biological reactions. This is for just chemistry in a jar. Chemistry in nature is a little more complicated. If you increase the temperature too much, biological reactions often stop. And that's because they're catalyzed by enzymes and proteins, and these things don't survive in high temp. Since it's the high energy collisions that result in the products, this also produces the faster rate. So higher temperature leads to higher energy molecules, higher energy collisions. All right, so to summarize, reaction rates will generally increase with increasing concentration, molarity, and with increasing temp. And reaction rates generally decrease as a reaction proceeds. So that let's just get that straight too. The initial rates are what we're talking about. So a slow initial rate versus an intermediate initial rate versus a fast initial rate. If we watch this reaction go on, the rate is going to go down because it's always going to be slower than how it started because there's going to be less reactants, right? As this reaction happens and goes forward, H2 is going down, I2 is going down. There's going to be less and less of that around. Okay. So the idea of dynamic chemical equilibrium is that a reaction can proceed in both the forward and reverse directions. And this is a reversible reaction. Now, in a chemical reaction, the conditions, or the condition in which the rate of the forward reaction equals the rate of the reverse reaction is called dynamic equilibrium. And this condition is not static. That's again with the term dynamic, because the forward and reverse reactions are still happening. They're just happening at a constant rate. Now, when dynamic equilibrium is reached, the concentrations of reactants and products don't change anymore. So the reactants and products are still being depleted. They're still being used up at the same rate that they got formed in. The difference is the concentrations remain constant. So I'll take a look at this set of, I guess, I want to call these diagrams. I always forget what we're supposed to call these little pictures, because they're not exactly diagrams, but they're not pictures either. They're representations of molecules. So I'm going to go with diagrams. I apologize. When the concentration of the reactants and products no longer changes, equilibrium is reached. So let's see when that happens. So in this reaction at time 0, we see that there's actually no product. HI is the product in this reaction. And at time 0, there's no product. It's all reactants. At time 15, we see that there is less of each of the reactants. There was 8 to start with, and now there's 6. And some product has formed. And I encourage you to take a minute to look at why there's 4 HI, and make sense of that to yourself. Then we see at time 30, more product has been created, more reactant has been used up. They are down to 4 H2s and 4 I2s, and now product is 8. And then at time 45, we see that nothing's changed. So from 30 to 45, the concentrations of these guys is constant. It's not changing. Yet the reactions are still happening. There is still product being made. There is still reactants being used up. So this is the indication that we've reached dynamic equilibrium. And this is what happens. Different reactions will reach dynamic equilibrium at different rates, at different times, depending on your concentration and temperature and all that stuff. But what is true is that for this reaction, doesn't matter. Well, actually, I'm getting ahead of myself. Let me back up. Let's continue. The equilibrium constant. This is what I wanted to tell you about right now, but I hadn't introduced it yet. So let's introduce it. So a way to quantify the relative concentrations of reactants and products at equilibrium is the equilibrium constant. Now, when dynamic equilibrium is reached, the forward rate is the same as the backwards rate, right? Sameness. Because these reactions are the same, the concentrations of the reactants and products don't change anymore. That's our constancy. The constancy of the concentrations of reactants and products at equilibrium does not imply that the concentrations of reactants and products are equal to one another, right? They're not. It just means that they are equal to the time. It just means that they're not changing, okay? Constancy here and sameness. Sameness is about the rate. Constancy is about the concentrations. But the main confusion students get when they talk about equilibrium is that the concentrations are equal to each other. They're not. Now, some reactions reach equilibrium only after most of the reactants have formed products. Okay, so like the equilibrium happens when almost all of the reactants are gone, like we saw in the previous example. Other reactions reach equilibrium when only a small amount of the reactants have turned into products. And so the amount of reactants and products depends on the reaction, and it can actually be expressed numerically with this equilibrium constant. So every reaction, even the two that we've looked at already, and this will be 3 now with this guy. Let's write these out. We've got H2 and I2 giving us 2 HI, and we also have N2O4 breaking down into 2 NO2s, or 2 NO2s forming to make N2O4. So in all 3 of these reactions, the equilibrium constant will be different. And no matter where you are in the world when you measure the equilibrium constant for this reaction, you will come up with the same answer. So, of course, there is a temperature dependence to this. So as long as you're at the same temperature, doesn't matter who is calculating the equilibrium constant, it'll be the same. So we can use equilibrium constants actually to identify what chemical reaction we're looking at, assuming that every reaction that we want to look at has been calculated already and put into a book somewhere that we could look up. Okay, so consider the general or this generic equilibrium reaction, where A and B are the reactants, C and D are the products, and little a, b, c, and d are the coefficients that would go in front. So those could be ones, they could be twos, just like there's a 2 here or a 2 here. And so the form of our equilibrium expression is going to take this. We're going to take the products and their concentrations, whatever those are, and we're going to put that on top. So one times the other. And if they have a coefficient in front, we're going to raise them to that power. And we're going to put that over the reactants, and we're going to do the same thing. We're going to take their concentrations of those, put them here, and then raise them to the power of their coefficients. This is going to give us a ratio of products over reactants. And you can already imagine, if we have more products than reactants, so if products is bigger than reactants, then our K is going to be bigger than 1. I should do it this way. Our K will be bigger than 1. If our products equal our reactants, then, if the two numbers in your fraction are the same, then K will equal 1. And if products are less than reactants, darn it. If products are less than reactants, then K will be less than 1, right? Because if the products, which are on top, is a smaller number than what's on bottom, you're basically dividing by a bigger number, you're going to get less than 1. So we can use this K, and I'll show you in a minute a better sort of summary of this, but we can use the value of K to give us an idea of how much product we get once this reaction hits equilibrium. And the reason that we want to worry about that is because if you leave a reaction unattended, it goes to equilibrium. Every reaction you start and walk away from goes to equilibrium. And so it makes sense that that's fine. That's fine. If you have a K that's really, really bigger than 1, then that's fine. Let's start the reaction and walk away, because when you come back, when it's at equilibrium, you're going to have lots of products, right? That's what KEQ being bigger than 1 means. If you have a situation, though, where your reaction you're working with has a K that's 1 or less than 1, then you don't actually want that to hit equilibrium, because when it does, you're not going to have very much product. And so we're gonna touch on that towards the end of this chapter, on how we can actually push a reaction to do what we want it to do. And you might think, well, why would you want to do that? Well, because sometimes the reaction sucks. It doesn't do very well. It has a low K. The K value is less than 1, meaning you're not going to get very much product from that reaction. And that might be a reaction you want to get a lot of product from. And so you don't want to let that one go to equilibrium, because at equilibrium you don't have very much. But again, the equilibrium constant gives you an idea of which reactions give you lots of products and which ones don't. Now let's try making one of these. Let's try writing one of these. And so you can see here I've got an equation for us to try. So this is 2 N2O5s. Now, by the way, you need to balance your equations before you try these. If it's not balanced, it won't work. Okay, so you need a balanced equation. So take a minute to make sure that you can see how this is balanced. Okay, so we're going to take the concentration of the NO2 raised to the power 4, concentration of O2 raised to the 1, or an implied 1, or not raised to anything, right? Because there was a 1 here, so it's just raised to the 1, over the concentration of N2O5 raised to the 2. And then you'd calculate it. Now here they haven't given us any numbers. Okay, they haven't given us any numbers, but we could set up the expression. Let's set up a few more expressions. So let's do this one. H2, I2, 2HI. So KEQ would equal the concentration of HI squared over the concentration of hydrogen gas times the concentration of iodine. Both of those raised to a 1, right, because there's a 1 in front. And so if we had numbers, we could calculate what the KEQ would be. Here's the other one. N2O4, 2 NO2s. So KEQ for this reaction would be products over reactants, products NO2 squared over the reactant, N2O4. And so remember, at equilibrium, we're looking at just how much of these guys are there and making a ratio. That's all this is. Okay, so for when KEQ is large, and actually I do have a couple of reaction numbers I can show you. So here's a large KEQ to look at. So there's going to be a high concentration of products and a low concentration reactants at equilibrium. So just to give you an idea, KEQ here is 1.9 10 to the 19. It's a 1 with 19 zeros after it. So that's a big number. We get a lot of product. Lots of HBr forms when this reaction happens, and there's only one reactant in this diagram, right? So that's what we're looking at. It's just a ratio of what's there at equilibrium when everything stops changing concentration. And then in this other one here, down here, N2O2, and making nitrogen monoxide. This one's a small KEQ, 4 10 to the minus 31. So this has 30 zeros in front of this 4. So it's a very, very, very tiny number. And so we're going to mainly see reactants and not a whole lot of products. It's funny how this one had more products in the diagram than this one had reactants, and it had a larger number. Okay. So yeah, just as an example. So to summarize, large KEQ, forward reaction is favored in that we're going to get lots of products. So when this thing, when the forward direction and the backwards direction finally settle out, we'll just have a whole lot more in the forward direction and not so much in the backwards direction. I kind of want to draw it like that. Now their rates are equal. They're at equilibrium. The rates of these two are the same. It just so happened though that this one went a lot further forward before it reached equilibrium. Okay, so that's what it means. When KEQ is much less than 1, the forward reaction is not favored, the reverse reaction is favored, and we have only reactants. And when KEQ is equal to 1, then neither direction is favored, and the reaction proceeds about halfway before equilibrium is reached. Okay, some exceptions. So the concentrations of pure solids and pure liquids are actually excluded from the equilibrium expressions. They are constant. They don't change at all. So calcium carbonate, solid, calcium oxide, solid, neither one of these is going to affect, or neither one of these is going to be an indication for us, or matter. What am I trying to say? We're looking at how things are changing, right, during the reaction. Since solids aren't concentrations, does that make sense? A pure substance isn't dilute or concentrated. So since these don't have concentrations, they're left out. That's what I'm trying to say. Liquids and solids are left out. So anything that has a little L in parentheses or an S in parentheses is left out. So if you were writing the equilibrium expression, it would only have the gas form in here, okay? Before we move on, you're going to wonder, why do we need to write equilibrium expressions? For two reasons. One, so you can calculate KEQ and tell me if a reaction proceeds forward or backwards. The other reason is because we're going to, remember I told you, sometimes we don't want equilibrium to happen. We want to be able to maybe push a reaction forward even though it wants to stop at not going forward. And so then we're going to need to know how to manipulate an equation, manipulate a reaction. And the KEQ tells us what we can manipulate. in a reaction. So for this reaction here, if we want to affect it somehow, make the rate faster or slower or favor the forward direction or the backwards direction, there's only one concentration that we can mess with that's going to do anything, and that's the concentration of CO2. And we know that because the KEQ has CO2 in it. Previous, we saw some KEQs like this one and this one. If we wanted to affect this reaction, well, we could mess with HBr or Br2 or H2 because they are part of the KEQ. So that's right. We need to have the KEQ so that we can calculate things, but also so that we can know what we can change or mess with down the line. Let's try doing one of these. So in this example, I've given you the equation and some of the concentrations. It's your job to write the KEQ and then to get the answer. So I would pause the video, give that a shot. I'm just going to go ahead and fill in the answers right here. All right. So hopefully you got 5, 10 to the 1, or 50 for that. So the question could be, does this favor products? Does it favor reactants? KEQ here is larger than 1, and so that means the forward direction is favored. We are going to get more products than reactants. Let's do another one. Go ahead and pause it. Give that one a shot. So here, we are given KEQ. Sorry, I probably should have prefaced that this isn't the same. Here, we want to know what is the concentration of carbon dioxide at equilibrium. So this reaction has gone to equilibrium. We want the concentration of carbon dioxide. So they've given us the KEQ. It's 2, and they've told us that this is at 1,000 degrees Celsius. It doesn't matter really what temperature this is at, because we're not going to be comparing it to anything. So let's just take it at 1,000 and do this. So we know it does favor the products. We just want to know how much CO2 there is. So we're going to need to rearrange this. And if you rearrange for CO2 using your algebra, right, we're going to get KEQ COF2 squared over CF4. So 2 and you should get 1.10 molar for the concentration of carbon dioxide. So again, putting an equilibrium expression together. These are also called mass action expressions, or equilibrium expression, and then rearranging it for CO2. I like to rearrange my formulas first and then plug in the numbers, but you could have done that however you wanted. Okay, let's talk about Le Chatelier's principle. Now, disturbing a reaction at equilibrium is called Le Chatelier's principle, and when a chemical system is at equilibrium and you disturb it, the system will shift in the direction that will minimize the disturbance. And your book uses a really terrible example about populations moving in and out of Middle Earth. I'm not a big fan of it. Let's just use a real chemistry discussion example. So in this diagram, we have that N2O4 and 2NO2 reaction that's at equilibrium. And so what we're going to do here is we are going to show what a disturbance looks like. So if we add NO2 to this reaction, okay, then we're increasing artificially the amount of product that there is. Okay, so now this thing won't be at equilibrium anymore, right? That's what it means. Equilibrium is when everything balances out to a point where. So let me back up. I don't want to lose everything that I just said, but I want to emphasize something that I was going to say. If you did this experiment, okay, at 1,000 degrees, but you used completely different. Sorry, not the two. The two would be the same. If you use completely different concentrations of everything, let's say that these were all like 10 times greater. So this was like 20.5 and this was 11.8 or whatever, or that's not 20 times, but whatever. They were just much bigger concentrations. Your KAQ would still be 2. It would still be 2. The actual concentration of carbon dioxide in your experiment versus the one that we just checked would be larger, but that's because the KAQ is always 2. So if you come over here to this reaction that we've disturbed now, the KAQ was something, whatever it is for N2O4, whatever this is, KAQ equals, okay? The KAQ is set. That's what it is at equilibrium, the ratio at equilibrium. So we come in here and we add NO2. We made this ratio much bigger now. So let's just make up a number just for fun. Let's say that this KAQ actually is 2, okay? And it's 2 because this number is 4 and this number is 2. So whatever we get at equilibrium, we found out that it was 4 for NO2 and 2 for N2O4, and so we put it into this equation, and KAQ is 2. So KAQ wants to be 2. So now we come in here, and we're adding more NO2 to it. Okay, we add more NO2. So we've artificially made this number on top 6. Okay, for whatever. So NO2 squared comes out to be 6 because we added more. Okay, well then, the ratio is not right anymore, right? This ratio is now wrong. This ratio is 3 instead of 2. And so nature is going to shift the direction of this reaction, the favored direction, until it gets back to an equilibrium, meaning till it gets back to a KEQ equaling 2. And we can see with some easy math what that means. It means that the number on bottom of our fraction here has to go up to 3. So however much N2O4 we had has to go up. Okay? Well, does that make sense that that's what's going to happen? Well, think about it. We added more NO2. The NO2 only does one thing. It reacts with itself to make more N2O4. So having more NO2 around is just going to make more NO2s collide with each other until they start to make more N2O4s. And then once there starts to be more N2O4s around, eventually we'll get to a point where there's enough N2O4s that they start to break down and make more NO2s again. But that's when we hit equilibrium again, right? And so the new equilibrium has happened. So we started off with an equilibrium of 4/2. Then we shifted something. We added products. We changed the top number to something bigger. So then nature has to increase the bottom number. Now, I'm just showing you this with math first so that you can kind of be certain that this is all true. But now let's just learn it the easy way. So when we add products, the reaction is automatically going to shift away from the side that we added things to. If we add products, it wants to make more reactants now, right? That should make sense. So it's going to shift to the reactant side. This is the reactant side, this is the product side. So adding NO2 shifts it to the product side. Let's look at a different one. What about if we were to, let's say, add N2O4? Let's add reactant. So if we go and we add more N2O4 to this equation, again, without going too much into the KEQ, NO2 squared over N2O4, right? If we've just made the number on bottom bigger, without changing the number on top, our KEQ is going to go down. So the only way that this KEQ would stay the same or get back to being the same is if this number has to go up as well. And so that's what's going to happen. We're going to add more N2O4. Lots of N2O4s around are just going to break apart to make more NO2s in order to establish that equilibrium again. So again, it always shifts away from the side you add something to. So if we add reactant, this is going to cause our reaction to shift right and make more product. Now, adding something to one side or the other is only one way that you can affect equilibrium. You can also remove something. If I come in here and I remove some product, what direction do you think it's going to shift? It's going to shift toward the side that we removed stuff from. So it shifts away from where we add things, it shifts towards where we move things, right? If we remove some NO2, now there's not as much NO2 as there was before, and we needed that NO2 to be combining together to make N2O4 in a way that the rates were equal. So now the only way that equilibrium can be reestablished is if some more of these N2O4s break down to get back to that equilibrium. So adding reactants or products will cause a reaction to shift away. Removing products or reactants will cause the reaction to shift toward that side of the reaction. A typical question will be something like, let's give you a better one. H2 plus I2 to HI. If I said, I'm removing I2, what direction is that going to cause this reaction to shift towards? And I'm sorry, there's usually forward and backwards arrows. Removing I2 is going to cause a this way shift. Coming back to that really small KEQ that we looked at, I apologize for my technical issues here. My iPad is clearly slow. Coming back to this reaction right here, this had a really, really small KEQ. So this is one of those where if you were interested in collecting some NO2, you don't want to let this go to equilibrium because that's not going to help. What can we do to make this reaction go forward more? Well, we could add lots and lots of N2 and O2, right? Adding more of this stuff is just going to keep causing it to make more products. Something else we can do is we can be removing the NO as it forms. We can figure out a way to let these react and let our product bubble into, let's say, a separate container where it gets funneled away so that this never builds up. If it never builds up, then it never hits equilibrium, and this just keeps going in the forward direction, forward direction, forward direction. So that's a way that we can exploit Le Chatelier's principle. Let's talk about how volume can affect Le Chatelier's principle or our equilibrium. So changes in volume of a gas or a mixture of a gas can result in a change in pressure. A decrease in volume causes an increase in pressure, and an increase in volume causes a decrease in pressure. So from the ideal gas law, PV equals nRT, we know that lowering the number of moles of a gas results in a lower pressure at a constant temperature and a volume. So a system can respond to disturbances by changing the number of moles of a gas that are present in order to relieve the pressure change. So because adding, decreasing the volume of this container increases the pressure, nature says, hey, if there's less gas, there's less pressure. So look at the reaction here. It's got 1 mole of nitrogen gas and 3 moles of hydrogen gas. So 4 moles of gas on one side of the reaction versus 2 moles of gas over here. So nature just said, hey, pressure went up a lot. We need to lower the amount of moles that are in here. I have 2 options. I can run this reaction more backwards and cause more of the ammonia to turn into nitrogen and hydrogen gas, which actually creates a lot more gas and more pressure, or I can run the reaction in the other direction, minimizing that number of moles and lowering the pressure back to something that's, back down into the equilibrium realm. And so that's what will happen. The reaction here will shift towards the side that has less gas moles. The opposite is true. An increase in volume causes a decrease in the pressure. So the only way to keep that pressure up is to shift the reaction direction so that more moles of gas is produced. And so here's another way that we can cause a KEQ. Again, let's say that this reaction had a low KEQ. If it doesn't proceed into the forward direction very well, hey, let's put it under pressure. Because pressurizing this system is going to cause nature to say, hey, I want 2 moles instead of 4 moles of gas. And so the reaction will proceed forward where it may not have proceeded forward before. So that's how volume can affect equilibrium. So again, to summarize, if a chemical system is at equilibrium, the effects of volume are as follows. Decrease in volume causes a shift in the direction that has fewer moles of gas. Increase in volume causes a shift in the direction that has more moles of gas particles. And so notice that if a chemical reaction has an equal number of moles of gas particles on both sides, then a change in volume is going to have no effect. I wanted to talk about how the developing fetus actually gets oxygen from its mother. So hemoglobin, Hb, in this reaction on top, reacts with oxygen according to this equilibrium. So hemoglobin plus oxygen give you oxygenated hemoglobin. Now this equilibrium constant is neither large nor small. Consequently, the reaction shifts towards the right or left depending on the concentration of oxygen. So it might make sense that as blood flows through the lungs where oxygen concentrations are high, that the equilibrium shifts to the right. And, it's right here. Shifts to the right and hemoglobin loads the oxygen and we get oxygenated hemoglobin. And then as blood flows through the muscles where oxygen concentration is low has been depleted, the equilibrium shifts to the other side and hemoglobin unloads the oxygen. So this is beneficial for us. This is how our bodies get blood around, right? Now there's a handoff actually. There's hemoglobin in your bloodstream that carries the oxygen around, and then there's myoglobin, which will live in the muscles and take that oxygen. So it doesn't just like dump it in your muscles, but it hands it off to a different carrier. Anyways, fetal hemoglobin, HbF, slightly different from adult hemoglobin. Hemoglobin is a tetramer. It has 4 protein chains. 2 of those chains are different in fetal hemoglobin, and the change essentially causes the fetal hemoglobin to have a higher affinity for oxygen. So there's a molecule called 2,3-BPG that reduces the affinity of oxygen in hemoglobin. In our adult hemoglobin, it binds to that BPG molecule pretty well, and so that it's a way of regulating the amount of oxygen that hemoglobin can carry. But babies don't have that, or fetuses don't have that binding to BPG. So they innately have a better hemoglobin for carrying oxygen. And so fetal hemoglobin will actually load oxygen at a lower concentration than adult hemoglobin. And so this is useful because when the mother's hemoglobin flows through the placenta, it unloads oxygen into the placenta. So nature has engineered a chemical system in which the mother's hemoglobin hands off oxygen to the baby's hemoglobin and not the other way around. They're not competing for it. The equilibrium constant, the KEQ for fetal hemoglobin is higher than for adult hemoglobin. KEQ is bigger. So that just means we get more of this than this when these 2 reactions are happening side by side. All right, let's talk about the effect of temperature on equilibrium. So in an exothermic reaction, we can think of heat as a product. Raising the temperature of an exothermic reaction, think of this as adding heat to the product side, okay, causing the reaction to shift left. In an endothermic reaction, we can think of heat as a reactant. So raising the temperature of an endothermic reaction, think of this as adding heat to the reaction side, okay? Sorry. Think of it as adding heat to the reaction side, the reactant side, causing the reaction to shift to the right. So back to the endothermic reaction real quick so you can see that. Heat, we can think of it since it's being given off as a product. And so if we add heat, right, it's going to shift away from that. But we can also remove heat and get it to shift forward. So there are reactions that are exothermic that will stop if it gets too hot, right? If that heat builds up, then they stop. So what we do is we find a way to pull that heat away, some kind of heat sink that'll just draw that heat away so that there's constantly a forward direction. So cooling a reaction will help it to proceed, and heating a reaction will help it to slow down in an exothermic sense. In an endothermic sense, it's the opposite of that. So with endothermic reactions, if you add heat, they go faster. If you remove heat, they go slower. And this is a really nice one to look at visually. We can see because N2O4 is colorless and NO2 is brown. And so we can really see here that as we add heat or warm up the solution, it turns brown. And so you can see here, warm temperature causes the reaction in this sealed tube to shift towards that NO2 molecule and a brown color. And then when we put that in ice, thereby removing the heat from the system, heat in this case is a reactant, and so that shifts the equilibrium back towards the reactant side, and so that brown product goes away, and we end up with more of the colorless N2O4. So a really neat system to be able to visualize these changes. All right, so to summarize, in an exothermic chemical reaction, increasing the temperature causes it to shift left, decreasing the temperature causes it to shift right towards the products. In an endothermic reaction, increasing the temperature, shift right, more products. Decreasing the temperature, shift left. Okay, let's shift gears a little bit and talk about solubility product constants. So a solubility product constant is kind of the same as an equilibrium expression, except that we are talking about solids dissolving into ions. So we would often show this for something like NaCl, right, and Cl minus, except we tend to say that there is no forward and backwards direction with NaCl, or at least we would say that the KEQ would be very, very, very large, way bigger than 1, because we're mostly going to end up with these guys, and we know we're not going to have a lot of these guys. But when we write the expressions for these, you'll notice that since the reactants are solid phase, then they are left out of the expression. So what a KSP is good for is actually letting us know what concentrations of these ions we can actually dissolve into a solution. So this is, if we want to make a saturated solution of, let's say, calcium sulfate, then all we need to do is look up the KSP for calcium sulfate. We see here that it is not very large, okay? We can then know, or then, once we have, let's say that we just dump a lot of calcium sulfate into some water, most of it settles on the ground, on the bottom. We want to know how much calcium sulfate there is. Well, if we know how much KSP, the KSP value, then we can figure out what these two concentrations are. So it's a way of knowing the concentrations of dissolved solids. We can also dissolve some solids and find out what the KSP is. So the solubility product constant, a large KSP is a compound that's very soluble. A small KSP means that the reverse reactions favored, the compound is not very soluble. And so again, we just omit the reactant because it's a solid form. You can look at the table here. You see that there's a measured, there's a table, right, for lots of different solubility product constants. I think your book actually has a more complete one towards the back. Let's do an example. Let's calculate the molar solubility of barium sulfate. So BaSO4.
SO4. And to do that, we're going to need to write an equation. So let's start with the equation. BaSO4, solid, forward and backward arrow, Ba2 plus, aqueous, and SO4 2 minus, aqueous. All right, so we write the expression. So KSP is going to be concentration of Ba2 plus times the concentration of SO4 2 minus, molar concentrations. So we can define the molar solubility. Your book likes to use a placeholder here. Since we don't know either of these, instead of X, your book uses S. But basically, since these are the same concentration, right, they're just S's, so we could say that this is S, this is S. So really this is S squared, right? It's or X. And you know, if there was a molar ratio here, like up here, 2 to 1, then there would have been a squared here, right? Then this would just be S, and this would be S squared. And then what would that be? S cubed, if we were really doing this. So we could figure these things out, or we could write, we could solve for, you know, using this method of just making these x's essentially. Just keep in mind that when you multiply things by squares, you get an extra, you know, so it'll be a cubed. X times x squared is x cubed is what I'm saying. Okay, and so then we want to undo this. So S is going to be the square root of KSP. Right? Square root of S squared gives you back S, and square root of KSP is what that is. And so then you have to go and plug all these numbers in. It's going to be the square root of whatever barium sulfate is. Is barium sulfate on here? 1.07 times 10 to the minus 10. Square root of that is going to be 1.03 10 to the minus 5 molar. So we see it's a pretty small number, and that's to be expected. The KSP for barium sulfate was small anyways. Of course, these tables are all temperature dependent also, so it's worth noting that. We could also calculate the molar solubility of anything on this list, right? Because we have to have these KSPs in front of us. On the exam, you might be given some concentrations, and it would be up to you to actually plug them in and solve the KSP. In fact, let me give you an example of that. So how would we solve a KSP? Let's see. What about a saturated solution of MgF2 has a magnesium 2 plus concentration equal to 2.6 10 to the minus 4 and a fluorine concentration equal to 5.2 10 to the minus 4. What would the KSP be for MgF2? So we would have to write the expression. The expression would be MgF2 2F minus, so Mg2 plus F minus squared, so 2.6 10 to the minus 4 times 5.2 10 to the minus 4 squared. So give that a shot in your calculator. I'll calculate it also right now. I like to start with my squared number first. So 5.2 10 to the minus 4 squared times 2.6 10 to the minus 4. So I get that the KSP is 7.0 10 to the minus 11. That seems to be pretty consistent with these, you know, values on here. We don't really know how soluble MgF2 is. We know that it is soluble because it's not on our not soluble list. But yeah, it's not a very good not a very large concentration. But that's what you might have to do on the test, right? Just calculate the solubility. Okay, one more thing actually on here. So because of the relatively low solubility product constants, water can actually easily become saturated with calcium carbonate and magnesium carbonate. So this is what hard water is. A drop of water becomes saturated with calcium carbonate and magnesium carbonate, and then the water evaporates. And this happens on your faucets, on your sink, on your cookware, on your cars and dishes. And so we can leave spots of calcium carbonate and magnesium carbonate as solid precipitates as the water dries out. Okay, so let's talk about enzymes. Oh, I'm sorry, catalysts. So the path of the reaction and the effect of the catalyst. So I showed you this already, this path of the reaction, and that there's something called activation energy or activation barrier. And for most chemical reactions, this energy is mainly the original bonds being broken and some new bonds being formed. And so for chemical reactions, the higher the activation energy, the fewer the number of reactant molecules actually make it over the barrier, and the slower the reaction rate. So in general, at a given temperature, the higher the activation energy, the slower the rate. And so are there any ways to speed up the slow reaction? Well, yeah, we know we can increase the concentration, which results in more collisions. We can increase the temperature, which results in more collisions and also higher energy collisions. But we can use a catalyst. And a catalyst lowers the activation energy or the activation barrier. And so let's just kind of look at how that happens. So here's an uncatalyzed reaction in black, and the same reaction that's catalyzed with a catalyst, something that helps the reaction go faster. So this catalyst will provide effectively an alternative pathway with a lower activation energy barrier. Catalysts can be acids or bases, they can be enzymes, they can be vitamins. I mean, that's just an organic molecule. They can be metals. Platinum surfaces can be catalysts, and they can do different things. They can help orient the molecules the right way. They can prepare the molecules by reacting with them to form more energetic intermediates. I mean, think about it. I mean, this is a terrible analogy, but let's say that you need to find a job, okay? You need to find a job, and you've got a nice house, and you've got a car, and you've got lots of food, and a phone, and everything already. So, you're kind of taking your time to find a job. So your job pathway reaction is kind of slow. Well, a catalyst would come in here like a tornado and take your house and your job away, and your food and your money and your phone. And so now you've got to find a job a lot faster. So that's what this catalyst did. The tornado was a catalyst in that it took away all your stuff to make you more motivated. But a catalyst might add a hydrogen to a molecule to make it more of an acid, more of an electron donor, a proton donor. It might remove a proton from the molecule or from one of the reactants to make it more of a Lewis base, an electron, a Bronsted base, a proton acceptor. Do you know what I mean? So chemically changing one of the reactants can help it to become more reactive. And so different catalysts have different ways of helping. Again, I'm going to show you how some, I think I'm going to show you, I'm going to show you what an enzyme does in a second. And then I'll tell you about ozone too, because that's a good example. So here's an enzyme pathway. So sucrase is the red line. Sucrose is table sugar, and you have enzymes in your body that can break down table sugar. Now, table sugar can also just break down in water. Water can break down table sugar. Now, the activation energy for that pathway is pretty high. And so, while sugar does dissolve in water, it often and does get broken down into its constituent parts, glucose and fructose. It doesn't happen very fast. So your body, though, makes this happen faster by using an enzyme, and an enzyme is just a protein that your body makes that, and the way that it lowers the activation energy is really, really cool. It goes and wraps around sucrose. It grabs it, right? Part of the enzyme holds one of these, part of the enzyme holds the other one, and then it literally pulls it apart. It pulls it apart to weaken the bond, because if you weren't pulling it apart, weakening that bond, then you've got a pretty strong bond, and water has to just come in here and break this on its own. But what sucrase does is it pulls on these guys, makes it a lot easier for water, and then water comes in here and breaks it. Hydrolyzes it. Hydrolysis is water cutting. So that's how enzymes work. Now, they don't all do the same thing. They don't always go and pull on the molecule to get it to weaken the bond. Sometimes they have a third spot, you know, in the enzyme. They call this the active site, where the molecule actually sits. There's a third spot which let's say that there's you know, A plus B gives you C, or let's make it like 2 A's and 1 B gives you C. Let's say this is A number 1 and this is A number 2, and we're just waiting for B, and that normally that takes a lot of energy for this to happen. Well, an enzyme might have a spot for B to sit in here, and so it just goes and gets A, and B, and now they're all just next to each other, all pointed the right direction, all waiting to just react, and then they react. So sometimes an enzyme just makes a spot for everyone to hang out close to each other. Sometimes it's a reaction. Sometimes it's an acid-base reaction. Sometimes it's, you know, pulling them apart or smushing them together. So enzymes are really cool. Other catalysts. Let's talk about a different catalyst. If I can figure out what's going on here with my slides. We got one more slide, so the last slide's probably the learning objectives. So let's talk about the ozone. So another catalyst that isn't biological is what happens with our ozone. And so upper atmospheric ozone, or O3, will actually react with oxygen to produce oxygen gas. Now, ozone is a shield against harmful ultraviolet radiation. So this non-catalytic destruction of ozone happens naturally. Okay. Now, we have protective ozone because the radiation has a fairly high activation barrier, and so this reaction proceeds at a fairly slow rate. The ozone layer does not rapidly decompose into O2. However, the addition of chlorine from synthetic chlorofluorocarbons that we used to use in all kinds of aerosols and in pesticides and in hairspray cans, so these, like this, we used to put these into the air. The chlorine acted like a catalyst. And if we take Cl plus O3, we get ClO and O2. And this first step in this pathway, the catalytic destruction of ozone, is very fast. So in the case of the catalytic destruction of ozone, this is happening much faster. So this led to a hole in the ozone layer. So we don't want this reaction to happen. The catalyst doesn't change the position of the equilibrium, only how fast we get to equilibrium. So there is ozone in our atmosphere that is, you know, breaking down into oxygen eventually, just like here's another thing, diamonds, right? Carbon in diamonds, carbon in solid breaks down into carbon dioxide. It just exposes you to air. Now, I'm pretty sure that this is not a equilibrium reaction, so I probably shouldn't even mention it. But this reaction, at least in the forward direction, happens. It's just super, super, super slow, which is great for us, right? Going back to the ozone, we want this reaction to be slow. We want ozone to protect us. But when you introduce something like a catalyst, you quickly degrade that ozone, and so that would be like, you know, all of your diamonds just dust turning into carbon dioxide much faster. You know, if it was like diamonds aren't forever, or diamonds are forever, but because we've poisoned the earth and there's all kinds of pollution, diamonds are only 3 years now. You know, I think we'd be more upset though about the ozone layer. Okay, so that's what I wanted to show you guys. So in review, chapter 15, we looked at equilibrium, the ideas about sameness and constancy, that the rate of the reaction in an amount of time that gets turned in, the rate of reactant into product, and how, I'm so sorry. I teach Chem 1A, and we go into rate law, and we talk about, you know, A plus B makes C, and that we define the rate of the reaction as the decrease in the delta A, right, per second or per unit time. I'm just trying to say right now that the rate of a chemical reaction is just the amount of reactant that goes into product in a given period of time. That's what the rate is. It's how much of A turns into C per second. Okay. Sorry, we go over the definitions in Chem 1A here. That's all we're saying. That's what rate is. How much product forms per whatever, per minute, per second, per hour. We looked at dynamic equilibrium, how forward rate equals backwards rate. We looked at the equilibrium constant, that for gaseous or aqueous reactants that are products and reactants, we can put them into a ratio and actually see if our reaction is a good one or a bad one for forming products. We looked at Le Chatelier's principle and how we can disturb a chemical reaction and how that reaction will reestablish an equilibrium and shift in a direction that minimizes the disturbance. We saw a solubility product constant, KSP, that describes the dissolving of ionic compounds. We can use that to figure out how much of a dissolved ion there is in a particular solution. And we looked at most chemical reactions must overcome an activation energy, and that catalysts are substances that increase the rate of a chemical reaction, but don't get consumed by it. And I don't think I said that earlier, but a chemical reaction does not consume a catalyst. The catalyst gets used in the reaction, and then it gets regenerated so that it can be used again. All right, so the learning objectives. I don't know why this is somewhat suggesting that there isn't another slide. Here we go. All right, guys. So hopefully these are helpful. Hopefully this points you in the direction of what you should study. I really recommend doing some of the problems from the book, just because there's a lot to practice. Do the ones in blue so you can look at your answers. But that's it. All right, guys. See you in the last video.